So here we have a dyno graph, and for fun, let's just take a look at where the power and torque curves intersect. So the red and blue curves seem to intersect somewhere around here. If we drop a line to the RPM axis, we'll see that they intersect somewhere in between 5 and 5.5k RPM. So I'm going to take a guess and say that they intersect somewhere around 5250 RPM. And if you're watching this video, this probably isn't anything new to you. In fact, this probably is the reason why you're watching this video, because you've seen this 5250 RPM number so often, right? Because you've seen so many dyno curves or dyno graphs, and you've always wanted to know why do they always intersect at 5250 RPM. Now, if you are new to this, then let me drill into your head why this 5250 RPM is such a special number. So here we have a completely different dyno graph from a 2018 Harley-Davidson Softail Fat Bob 114. But either way, let's just take a look at where the torque and power curves intersect. So intersect somewhere here, drop another line to the RPM axis, and you'll see that sure enough, they intersect around 5250 RPM. So this is in fact a special number. And I'll show you one more graph so I can maybe drill it into your head that this really is something worth talking about. So here's our final graph. Again, we'll do the same exercise. We'll just take our torque and horsepower curves, see where they intersect somewhere around here. We'll drop another line, and sure enough, you'll see that they intersect somewhere around 5250 RPM. So hopefully sample size of 3 is enough to convince you that this 5250 RPM is not a fluke. There's something going on behind the scenes that is probably worth talking about. Now if you were to zoom into each of these graphs, you would see that the 5250 number actually is precisely 5252 RPM, and this 5252 number shows up so many times over and over again, no matter what dyno graph you look at, that it begs the question, why do torque and horsepower always cross at 5252 RPM? And the answer lies in a pretty basic physics equation. The basic physics equation in question is power is equal to torque times angular velocity. And really quick, this equation comes from an even more basic equation, which says that work is equal to force times displacement. But obviously we're not working with linear force and linear displacement, so we're going to need to use the rotational analogs of those things. And the rotational analog of force is just torque, and the rotational analog of displacement, linear displacement, is just the angle you swept through. So we can say that work is equal to torque times the angle you swept through. If you divide by time on both sides, you'll get that work divided by time is equal to torque times the angle divided by time. Knowing that power is just defined as work divided by time, and knowing that angular velocity is literally angle divided by time, we can say that power is equal to torque times angular velocity. And more formally, you'd arrive at this equation by differentiating with respect to time, because in real life, angle might not vary simply with time, and so you need to use derivatives. But that's a topic for calculus, and if you want to know more about that, you can read up on derivatives a little bit. But yeah, so this is the equation we're going to be using for the rest of the video. But we have a massive problem, and the problem is, in this equation, power is equal to watts, torque is in Newton meters, and angular velocities in radians per second, which are not units that we use when we're talking about dynos. What we actually need is for power to be in horsepower, torque to be in foot-pounds, and angular velocity to be in revs per minute. So I'm going to define some new variables real quick so we can differentiate between power and watts and power and horsepower, and between the quantities and metric and the quantities and units that we're actually going to be using. So for the video, I'm going to say that H is equal to our power and horsepower, capital tau, which looks like a T, but technically it's a capital tau, bear with me. But we're going to say a capital tau is equal to foot-pounds, like torque in foot-pounds, and we're going to say that capital omega is going to be angular velocity, engine speed in revs per minute. And from Google, we can get some conversion factors. So from Google, we know that 1 horsepower is 745.7 watts, 1 Newton meter is 0.7376 foot-pounds, and for 1 radian per second, well, we can use basic geometry to figure out what that is in revs per minute. We don't need Google for that. From the conversion factors we have at hand, if we know that 1 horsepower is equal to 745.7 watts, that means if we have H horsepower, we gotta have 745.7 H watts. And we've defined P in our earlier slide to be power in watts. So from this relationship, we know that P is equal to 745.7 H. And from our second conversion factor, if we know that 1 Newton meter is 0.7376 foot-pounds of torque, then if we have tau Newton meters, then we must have 0.7376 tau foot-pounds of torque, which is going to be equal to our capital tau. And that's because we've defined capital tau to be torque in foot-pounds. So from this equation, we'll get that tau is equal to 0.7376 times little tau. And rearranging a little bit, we'll find that little tau is equal to capital tau over 0.7376. Let's focus on little omega for a bit. We know that little omega is engine speed in radians per second, but we want to convert that into revs per minute. So if we know that we have little omega radians per second, if we multiply it through by the conversion factor 1 revolution per 2 pi radians, and by the way, this conversion factor comes from the fact that if we sweep through 1 revolution of a circle, you would have swept through an angle of 2 pi radians. There are 2 pi radians in one full circle, essentially. So that's where that comes from. But if you multiply it through by this conversion factor, the radians at the top and bottom cancel out. And we're left with revolutions per second. But we need to take that second and convert it into minutes. So multiply by 60 seconds per 1 minute, and this factor comes from, well, the fact that 1 minute is made up of 60 seconds. There's not much to justify here. But the seconds cancel out, and we're left with revolutions per minute. So this means that a little omega radians per second translates to 60 times little omega over 2 pi revs per minute. And that's going to be equal to our big omega because we defined big omega to be our engine speed in revs per minute. Simplifying that equation a little bit, we get that big omega is equal to 30 times little omega over pi. I just divided the top and bottom of the fraction by 2. And with that equation, we can say that little omega is equal to pi times big omega over 30. So we finally done it. We've expressed our metric units in terms of units that we're actually going to use. And taking our equation, which is in metric units by the way, taking the equation power is equal to torque times angular velocity, where power is in watts, torque is in Newton meters, and angular velocity is in radians per second, we can just substitute P, tau, and omega for the equations we just came up with in the earlier slides. So performing the substitution, we get that 745.7 H is equal to capital tau over 0.7376 times pi times big omega over 30. So now if we take this equation and simplify it a little bit, and by simplify I mean just combine all the numbers together and get something more easy on the eye, we'll get this equation. And now we're ready to ask the question, what actually happens? And what actually happens when torque and horsepower cross? And this seems like a simple question because it is. It's really simple. They're the same number, right? That's what it means for torque and horsepower to cross on a graph. They happen to equal the same number. So if they're the same number, we know that capital tau is equal to h, which are both equal to some x. Do we know what x is? No, we don't. We have no clue what x is. It could be 2, 7, 29.3, who knows? But we know that they're both equal to x. And that's all that matters. And now we are at the home stretch. If we take our equation that we just found and we take the equation which states that tau is equal to capital tau is equal to h, which is equal to x, well, we can take the second equation and substitute x for both capital tau and h. When why? Because we've literally said capital tau is equal to h, which are both equal to x. So making the substitution, we get this equation and we can cancel out x from both sides, right? And from that, we'll get that 745.7 is equal to capital omega times pi over some ugly looking number. And what's really important to recognize is that this equation is the only unknown in this equation is capital omega. What's important to recognize is that if we're able to solve for capital omega in this equation, we will have found the RPM at which torque and horsepower are guaranteed to be equal to each other. So that's something big. Now solve for capital omega. Fortunately, this is a really easy equation to solve, and to solve it, well, We can just multiply through by 30 times 0.7376 and divide by pi. So our capital omega, engine speed in RPM, is going to be equal to 745.7 times 30 times 0.376 all over pi. And this should be the RPM at which torque and horsepower are guaranteed to cross. And plugging these numbers into a calculator, we get that capital omega has got to be equal to 5252.384 RPM. And ladies and gentlemen, we've done it. We have mathematically come up with a number at which torque and horsepower are guaranteed to cross no matter what you're testing, no matter what engine you're testing, no matter what happens. Really, this is like a universal constant almost. And now you know how you can come up with this number mathematically from first principles. And I think that's pretty cool. So if you like this video, feel free to like. If you didn't like it, feel free to dislike, but kindly let me know what I could have done better. And if you do like what I do on this channel, consider subscribing, and I'll see you in the next video.